My name is Evan Winter. For our project, I worked on film fabrication and characterization along with analytical calculations.
Hi, my name is Dylan Kirsch, and for this project I had two primary responsibilities: to characterize our novel materials and fabricate our prototype films.
My name is Allison Orr. For our project, I primarily worked on the analytical calculations in order to support our characterization and simulations with theoretical background.
Hi, I'm Joe Morgenstern, and I worked on the porosity parameters for CFD and FEA analysis.
Hi, I'm Spencer Crankle, and I worked on our CFD and FEA simulations that we looked to couple with our analytical calculations in order to determine the performance of our material.
Catalytic converters play a major role in reducing the harmful gas emissions that pollute our environment. With climate change underway, it is important that society works to prevent further destruction of our environment. The most common application of catalytic converters is in the automobile industry. Current methods utilize membranes made from exotic materials such as palladium. A novel alternative membrane technology is the use of so-called holy graphene as a membrane material. This material is formed by partially oxidizing graphene in order to introduce nanoscale pores that result in selectively porous material. The heat resistance and high surface area of the material make it an ideal material for this type of application. Our team chose to explore the viability of using holy graphene and palladium-doped holy graphene composite thin films for catalytic converter applications. Throughout this project, we intend to better characterize both pure holy graphene and palladium-doped holy graphene properties that could be suited for catalytic converter applications, and use simulations and computer modeling as well as analytical analysis to evaluate the feasibility of our idea.
The palladium-doped holy graphene sample is made via a thermal decomposition process, in which holy graphene powder and a metal salt are mixed in a ball milling process, which removes the compressibility of holy graphene. This mixture is then subjected to heat, leaving a metal-doped holy graphene sample. This sample must be mixed with undoped holy graphene to restore the compressibility. Through a collaboration with NASA, we received two palladium-doped holy graphene samples with varying ratios of doped to undoped holy graphene. The dry pressing process is extremely important for our project. Holy graphene is the only compressible graphene material. This is due to the through-thickness nanopores which allow the escape of trapped gas during compression. This process involves placing about 60 milligrams of holy graphene into a pressing die and subjecting that to hydraulic pressure for several minutes. The applied pressure can be varied to alter the apparent density of the film. We chose to press our films at both 3.6 and 9 metric tons.
The two samples we received from NASA differed in their ratios of holy graphene to palladium-doped holy graphene. The ratios are 1:1 and 1:5 respectively. Using scanning electron microscopy, energy dispersive X-ray spectroscopy, and transmission electron microscopy, we studied the nano and micro scale morphologies of these powders. Due to the limited quantities of doped holy graphene and the destructive nature of nanoindentation testing, we used holy graphene films pressed at 3.6 and 9 metric tons to obtain the mechanical properties.
In the transmission electron microscope, the 1:1 ratio holy graphene to palladium-doped holy graphene sample shows multiple particles of approximate diameter of 20 nanometers on the flake surface. In contrast, the 1:5 ratio doped holy graphene sample exhibits much higher concentration of particles that are much more uniformly and homogeneously distributed across the flake surface. Using image J, we found the average particle size on this doped holy graphene sample was approximately 18 nanometers, slightly smaller than the 1:1 ratio sample. As a result, we have decided to use the 1:5 ratio doped holy graphene powder in our prototype membranes and all future characterization. In the scanning electron microscope, the 1:5 palladium-doped holy graphene powder once again exhibits numerous particles on the surface. Many of these particles are actually too hard to see using only scanning electron microscopy, which is why we initially used transmission electron microscopy to narrow our material selection. In addition, energy dispersive X-ray spectroscopy of a highly doped holy graphene flake confirms that palladium is the element present on the surface, as shown by the elemental maps adjacent.
Nanoindentation is used to determine the Young's modulus and hardness of a material. For our project, only the Young's modulus is relevant. Atypically, we used a 90-degree 20-micron conical indenter tip due to the heterogeneous surface of the film. A larger tip gave us a better representation of the Young's modulus. We performed 5 indents across the surface of the 2 films and found the average value of Young's modulus for the 3.6 and 9-ton pressed films to be 7.38 and 12.43 gigapascals respectively. The images on the right show the 3-dimensional tip surface scans before and after indentation. The conical tip indent can easily be seen in the lower image.
For our computational fluid dynamics, we started with the 3D model of our membrane inside a tube, simulating an exhaust pipe. We then set the boundary conditions and parameters for the gas, porosity, and result control. For the gas parameters, the kinematic viscosity and density of carbon monoxide were used. For the boundary conditions, different initial volumetric flow rates ranging from 0.75 liters per minute to 750 liters per minute were used. We then set the porosity parameters based on coefficients from our Darcy's law calculations. Each simulation was run for 1,000 seconds, giving us convergence plots, solution fields, and area integrals. The results showed that the pressure gradient increased with increasing film thickness. This can be seen in the solution fields. The area integrals showed that outlet flow did not vary from initial flow, even with varying thicknesses. This means that due to the porous nature of polygraphene, the gas flow is relatively unimpeded, even with the thicker films.
Once the CFD was completed, the team utilized SimScale again to perform finite element analysis, or FEA, on the films to determine the mechanical stability under varying conditions. The team modeled 6 films ranging from 120 microns to 400 microns. For our material properties for FEA, we utilized the properties determined through characterization for the 9-ton holygraphene pressed film. A Young's modulus of 12.44 gigapascals and a density of 1,400 kilograms per meter cubed were utilized. We held the edges of the film fixed as boundary constraints. We then utilized the maximum pressure applied on each film from CFD and applied it to the top face of the films. The 2 key results from FEA were linear strain and displacement, which can be seen as solution fields. As the pressure was applied in the negative y direction, the greatest displacement was also in the negative y direction. Displacement in the x and z directions were minimal. However, the strain was greatest in the x and z directions. Past research by Hahn showed a failure strain of 2.2% for similar films. Therefore, our films all demonstrated the necessary mechanical stability to withstand varying flow rates.
In conclusion, electron microscopy was used to determine that the 1:5 ratio doped holygraphene has a more uniform distribution of smaller nanoparticles. EDX showed that the particles on the film are composed of palladium. Nanoindentation was used to determine that Young's modulus increases with increasing pressing pressure. This information was used to simulate our films using CFD and FEA. Our simulation showed that output flow rate is independent of film thickness and that mechanical stability generally increases with increasing thickness. Thus, the film we would use in future studies would be a 400 micron thick film when we hope to experimentally test a prototype device. Thank you for watching, and we would like to thank the following people for their support throughout our project.